Hey everyone, my name is Sam, and I'll be working with Grace, Matthew, and Param as we go through our Turbo Machines video project. Within this video project, we're going to be going over two of the main types of turbo machines. That is going to be the pumps and turbines. And within these two subcategories, we're going to be going over different examples and how they are applied. So, what makes a pump a pump? A pump is a turbo machine that adds kinetic energy to a fluid by either increasing its pressure or velocity, and there are multiple examples of pumps, like axial, centrifugal, a diaphragm, or even a piston pump. But the most common type of pump is a centrifugal pump. And to go to the figure to the right, is you can see a little design of one. It has an impeller, an eye, housing case, and discharge. So with the eye of the turbo machine, it sucks in a fluid. The fluid rotates radially and increases its velocity and then discharged. These pumps can be described in multiple different ways: the number of eyes it has, the number of impellers it has, and the blade angle. If there are multiple impellers, it's considered a multi-stage centrifugal pump, and that is ideal when you want to increase the head pressure off your pumps. You can calculate the ideal head loss with this equation below, but just know there's assumptions made to where it's actually above the actual ideal head loss equation. So when calculating head loss and the efficiency, we have this chart that we can look at, which is called the pump performance curve. And each graph is specified to a certain pump, certain type of pump, the RPMs that the impeller has. And so there's an equation that we can have, which is power gain, the fluid over the shaft, or the torque of the pump itself. And so this efficiency is always maximized at the design or normal flow rate. Here we can compare three different type of pumps. To the left, we have that centrifugal pump that I was illustrated before, and then the diaphragm pump in the middle, and the piston pump to the right. This centrifugal pump specifically is for a car engine, which increases its air flow rate and also increases the combustion rate for the gasoline.
So what you see right here is the space shuttle. And interestingly, in terms of liftoff thrust, this was actually the most powerful rocket to ever fly. So those three engines in the middle, those are liquid-fueled RS-25 engines. Now the big flamey things you see on the sides, those are the solid rocket boosters. They're basically just a giant candlestick. We're not going to worry about them. But those engines in the middle, which you can hardly see against the massive fire coming off of those solids, those are basically just giant turbo pumps. So we can actually go and calculate the energy that would be required simply to run the coolant system on those things. So anyway, we can do the math here and we can plug it into the Bernoulli equation. We can assume negligible body force and heat loss, and we get that it would take about 54.3 kilowatts of power to run a single coolant pump on one of these RS-25 engines. Now to put that into perspective, that's about 45 houses worth of power.
So let's move on to turbines. Turbines are a type of turbo machine that removes energy from a fluid. Now I'm going to be covering impulse turbines specifically, and Grace is going to be covering reaction turbines. So impulse turbines are not entirely surrounded by the working fluid and have negligible pressure and fluid velocity changes across the buckets radially. Now impulse turbines are most efficient with larger head and slow-moving fluids. So think larger head kind of means larger body, so think of a river. Now, a common example is a Pelton wheel. Now, impulse turbines use tangential fluid flow, unlike other turbo machines, and the ideal bucket shape will not add any radial velocity to the fluid. Now, as you can see from this graph, the theoretical max power generation of the turbine is at half the incoming fluid velocity.
Now let's talk about reaction turbines. Reaction turbines are most efficient at lower head and higher flow rate situations. These turbines are surrounded by casing, completely filled with working fluid, and the fluid experiences pressure drops along the moving blades. The degree of reaction for a typical reaction turbine is between 0.1 and 0.7. Francis turbines and Kaplan turbines are two examples of reaction turbines. Francis turbines have radial and mixed flow, and it is most efficient at medium head. Kaplan turbine has axial flow and is most efficient at very low head. The difference between impulse turbines and reaction turbines is that impulse turbines only has impulse force, while reaction turbines have both impulse force and reaction force acting on the blades. Reaction force is caused by the pressure drop and velocity change of the working fluid along the blade. Next, we will talk about turbine type selection. Calculating the power-specific speed using this equation can give an indication to what type of turbine is most efficient. On this graph, the power specific speed is plotted against the efficiency. As you can see, the Francis turbine is most efficient over a wide range of values. Therefore, the Francis turbine is most widely used. In real life, turbines are used in many places. Turbines can be used in electricity production, powering ship propellers, and harnessing renewable energy.